2004 question 10b. A particle is projected vertically upwards with initial speed of 2 g meters per second in a medium where there is resistance of kV squared newtons per unit mass. The first thing we have to do in these type of questions always is to draw a force diagram. And we notice that the only force that's explicitly mentioned is this resistance force, kV squared per unit mass. Per unit mass means per kilogram. So if you had, for example, 2 kilograms, the force would be 2 kV squared, or if you had 3 kilograms, it would be 3 kV squared, and so on. In this question, the mass is not given to us, so we can call it m, and therefore our resistance is m kV squared. So on our force diagram, we'll first of all draw the object. Let's put it in here and put in our forces. M kV squared is the resistance force. Go back to the question, we'll see that there is no other force actually mentioned, but in cases like this we have to assume that weight is acting downwards. Weight is always acting downwards on any object, and this weight is given by mg. So you would be expected to put in mg even though you're not explicitly told to put it in. So mg is the weight downwards. Next thing to always do in these questions, indeed in most applied maths questions, because vectors are nearly always present in these questions, is to get your directions clear. And you need to establish which way is forward or which way is plus. And if we're throwing this thing upwards, well, it's natural to call the upwards direction the plus direction. And this becomes very important later, so we don't make mistakes with signs with forces. Now, it turns out that these are actually the only forces on the object. Even though it is moving upwards, there actually is no force pulling it upwards. There was an initial force which caused it to move upwards in the first place, but that's now gone. And we're interested in all instants of time after that initial instant when it was fired. So if you like, you can just emphasize that by putting in, you don't have to do this, but just put in a force of 0 upwards. And this is now the complete force diagram for that object, that mass m. And over here on the right, we will just list the method, the different steps in our approach to this question. So step 1 would always be to draw a force diagram. And this leads nicely to the next step. If you do the force diagram correctly, the next step becomes easy, because the next step is to apply Newton's second law to the force diagram. And Newton's second law, F equals ma. Because upwards is the positive direction, we'll take that as the plus direction for our force, and the equation becomes F equals ma, or 0 upwards minus the two forces pulling against you, m kV squared and mg. That's your overall net force, equals ma. The m's cancel all the way across. We can tidy up by saying that acceleration is equal to minus into kV squared plus g. At this stage in the question, we have to always make a decision about a substitution for a, and this means we need to go back to our theory for a second. Acceleration by definition is the rate of change of velocity, which is dv dt. By the chain rule of differentiation, we can rewrite this as follows. It's dv dt, and we can put in a ds above and below. And again, by definition, ds dt, rate of change of displacement, is called v in our notation. So it's v dv ds. This gives us two ways to write acceleration, dv dt or VDVDS. And at this stage in the question, we always have to decide which of these two to substitute in for acceleration in our formula. And the way you know is by going back to the question and taking note of what variables are mentioned. And here we see that they mention height, which in our notation is s. They also mention speed, which in our notation is v. So if they mention s and v, that suggests that we have to use VDVDS. That's how you know. So VDVDS is the way to go forward here. VDVDS is equal to minus kv squared plus g. Once you get to this step, you're back to the three steps that we always follow in question 10 part A. And just to remind you what those are: number 1, separate your variables; number 2, integrate; and number 3, initial conditions or limits. First step is to separate. And by separate we mean keep all the v's on one side and keep all the s's on the other side, because they are the two things that are changing here, v and s. VDV, and under the line we're going to have kv squared plus g. And on the other side we're going to be left with minus ds, because ds multiplies across. And that's the first step already done. Separate. Now we integrate both sides. Put your integral sign over here, and also here the minus goes outside because it's minus 1, a constant. We should be able to recognize this from our maths course as the substitution method for integration. Let u equal to what's below the line. U is equal to kv squared plus g. du dv is equal to, the 2 comes on in front because the k is a constant. It's like number 2 or 3. It's like any other number. 2 times k v. And when you differentiate g, of course you get 0 because g is also a constant. Now for substitution to work, we need to end up with what's above the line here, VDV. That means get VDV on its own down here, and everything else on the other side, VDV. And you get du over 2k. And back to here, and put it back in. Integral VDV now becomes du over 2k. With 2k outside as its constant. And under the line kv squared plus g is u, equals minus integral of ds. Let's finish off our integration then. It's 1 over 2k. That now becomes the natural log of u, equals minus s. When you integrate the s, you just get s. And now that we've done that, we can put back in u. So that becomes 1 over 2k natural log of kv squared plus g. Minus s. That's the second step. Finished. We integrated both sides. Now we're on to the initial conditions or limits. So that will be covered in the next video.